Hello everyone, my name is Jubayer and I'm going to show you how to exfiltrate Onchip SRAM. This is a joint work between me and my advisor Matthew Hicks, and we are from Virginia Tech. Embedded systems and smart devices are everywhere. We use them for all kinds of things. We use them for security and privacy critical applications such as banking, home and industrial automation, and also sensing. Smart IoT devices are getting smaller and ubiquitous, commonly referred to as smart dust, which are making computers embedding the world around us. This makes physical attacks very real threats which we must protect these devices from. In addition, a lot of unfortunate and terrible things happen to such devices, for example, loss and theft. These devices are vulnerable to so many different attacks such as bus probing, fault injection, side channels, and cold boot. Cold boot attacks showed us that although mass storage devices such as flash are off limit due to disk encryption, an attacker can still break into system by using physical attack methods that freezes memory in a volatile dynamic RAM. That is, because we have disk encryption methods, attack surface has reduced from such that the attacker's focus moved to DRAMs from typical mass storage devices. Cold boot attack model aligns with our attack. So to refresh your memory, I'm going to summarize the attack quickly. First, we capture a live system and cool down its DRAM, which would obviously slow down the discharge rate of the DRAM cells. And we remove the DRAM once we're sure that the discharge rate is sufficiently reduced, and then place it into another machine which would allow us to analyze the DRAM content for different software execution states and the data of the victim machine. There are a lot of methods to prevent DRAMs from cold boot and bus probing type physical attacks. For example, scrambling and encrypting outgoing data. Anything that goes out of the chip must be encrypted, and DRAM level defenses. DRAM level defenses are not necessarily applicable to lower end embedded devices because of the harder cost and newer implementation requirement. So to provide software-only defense, there are numerous research that advocate using on-chip computation model, meaning keeping the security sensitive state within the chip in plain text, and whenever we need to send anything outside of the chip that is security critical, we encrypt them. This is a great solution because this pushes the sensitive data to the on-chip memories from DRAM, and that reduces the attack surface further. This is a schematic diagram of an SRAM cell which stores data using positive feedback between these two inverters, cross-couple inverters. It requires no maintenance, is very fast, and bistable startup, meaning some cells will power on into logic 1 while others will power on into logic 0. Uninitialized SRAM states look like this. If we have a large SRAM array and we plot the values before the system wrote anything on it, we'll get these values in the SRAM, ones and zeros scattered all over the SRAM. Here is a takeaway message from all this. An SRAM cell will retain its value if there is power in the bus. We don't need to maintain, we don't need to refresh. As long as there is power, sufficient power in the bus, the data will be there. Researchers tried to attack SRAMs using cold boot, but they mostly stayed within standalone SRAM type, that is discrete SRAM types, because attacking on-chip SRAMs provide us with many hurdles. We'll talk about that in a moment. We got this graph from a recent paper where researchers executed a data freezing attack, aka cold boot attack, on small microcontrollers. Once frozen, we need to remove power from the device and bring the power back quickly within a few milliseconds, meaning just power cycling it as quickly as possible because SRAM's data retention is rather short. The issue with that is how to do that physically, because think about a device with a battery. And then on top of this, an SRAM cell's retention time depends on fabrication technology, which determines the minimum temperature needed to freeze the data. So even if we can, say, power cycle a device within 20 milliseconds, we see virtually no data retention at most SoC's minimum temperature limit, minus 40 degrees Celsius. Another reason is why it is hard to attack on-chip SRAM is the placement of the SRAM. They're located in the die of the processor. So attacking them physically is rather difficult because it requires extensive technical expertise like decapsulation and focus ion beaming, etc. We executed cold boot attack on a Cortex A72 core from Broadcom at minus 40 degrees centigrade, meaning we brought down the device's temperature to minus 40 C, which is the SoC's hard limit according to the datasheet and information available online. We observed virtually no data retention, and the accuracy, as you can see from the table, is terrible. So on-chip SRAMs provide strong security guarantees for data and software as far as physical attacks such as bus probing and cold boot attacks are concerned. We present Volboot attack that overcomes all these hurdles and challenges on-chip computation methods security guarantee. Our attack has no dependency on temperature or the fabrication technology of the SRAM, and we do not have any time limit how fast we need to power cycle a device. Before we get to the details of the attack, let us skim through the threat model first. It is like cold boot with a target being the SRAM instead of DRAM. The device must be physically accessible to an attacker and needs some form of method to get to the SRAM, meaning you have to read the SRAM somehow. It could be debugger, it could be intermediate firmware, but still the assumption is DRAM and other mass storage devices are off limit to an attacker. We exploit power domain separation and expose power supply pins to launch our Volboot attack. Modern SoC's power distribution network is clustered and divided into domains. These domains are separated using power gating to allow efficient power management and startup and runtime. The domains are sometimes combined into bigger blocks and then exposed to the outside of the chip, as the requirement for these domains could be very different as far as power is concerned. The voltage level could be different and the current requirement could be different. We see three domains here in this illustration: core, memory, and I/O. Core has caches or registers, and sometimes caches or other kind of memory such as on-chip RAM, IRAMs. They have separate domains. If we maintain an external probe at the same voltage level as the operating condition of the chip and shut down the entire system, we create sort of a power island and retain memory state across the power cycles, meaning we are remembering the state of the SRAM from the prior computation state. Leaving these domain pins exposed is an important circuit design and architectural design choice, because the passive components such as capacitor or inductor required to stabilize the supply noise is prohibitively expensive if we place them on chip, but we need them to provide cleaner and reliable power to the SoC. Hopefully we understand the fundamental at this point, and now I'm going to explain how to actually execute the attack when we capture a device live. First, we need to determine the target domain and its associated pins, and then we measure the voltage of that pin and place a probe at the same voltage level. The probe must be capable of driving large current, because it obviously depends on the SoC itself how much current the pin is going to draw, but it's better to be safe to allow 2 or 3 ampere current draw, just to avoid any kind of retention failure during the system shutdown, and then we abruptly disconnect the power from the whole processor and the reboot with a firmware that allows reading target memory. We do not need to load any program unless the debug interface is fully disabled. Finally, dive into the memory and see what we get from it. We designed 3 proof of concept attacks in 3 different types of memories. For registers and caches, we targeted 2 Broadcom SoCs that come with the standard Raspberry Pi 3 and 4 and IMX 535 multimedia SoC from Freescale. They represent headless embedded device to full-fledged systems. The picture shows where to probe in these boards, and table shows different parameters of the test points. We executed the attack both in bare metal and OS setup. Here, let's look at how Volvoot works in a system where operating system is installed and we're trying to read the cache. Before I explain this experiment, let me elaborate on how to get cache data regardless of cache line's validity. These days, different CPU architectures allow cache access directly. For example, Cortex A72 and A53 allow RAM index operations and direct memory access to read caches respectively. When we reboot the device after power cycling, we introduce an intermediate firmware that stops the CPU from booting the kernel and enabling caches. This firmware executes CP15 coprocessor instructions to dump whatever is in the cache. We wanted to see in each moment of the attack or each attempt of the attack how much data we can extract from a D-cache. In a Linux environment, we created a user application that binds itself to each core when it runs. So basically, it's creating 4 instances of the same application, one for each core. It's a quad-core Cortex A72. The application contains a data structure of variable size ranging from 25% of the cache to 100% of the cache. When the data structure size is smaller, we can retrieve full data structure. As expected, when the data structure is comparable to the cache size, we start losing data due to eviction by the background process and the kernel itself. There are a few on-chip computation methods like tracer, for example, proposed to store security states in infrequently accessed registers like vectors and debug registers. We write different patterns in vector registers and compare the pre and post attack values of these registers to see if they match. Both Broadcom SoC retain all 32 vector registers value. Note, caches and registers, both type of memories, belong to the same domain for these two SoCs. Volvoot attack portrays a similar scenario when target is IRAM, internal RAM of an SoC. The domain for this memory is not same as cache and registers that we have seen so far. And note that we executed the attack on an IMX 535 multimedia SoC. This is an interesting device because it requires no software to read SRAM. The JTAG is opened before the system software is loaded. We filled out the IRAM with copies of image and execute the attack, and the graph shows the mismatch between the retrieved data. We retrieved 95% of the data, and the error came from the fact that the boot ROM uses and erases about 5% of the IRAM before we can get our hands on the memory. We can see that from the first and the last image. This is not retention accuracy though. This is the amount of data available to an attacker. Data retention is still 100%. Let's talk countermeasures now. Eliminating power domain separation is a solution, but it's not a sound one because, well, the power domain separation and exposed pins are there for a reason: performance and efficiency. Second, residual memory purging at the attack time will stop the Volvoot attack, but we're abruptly turning the system off, kind of starving the system from power. So It's not a reliable solution, and the system itself, including hardware and the software, will not have enough time to react to the attack. The next one is probably the most effective one, where the SoC resets the SRAM states at boot. By default, most SoCs don't execute such routine because it reduces boot speed and prevents security applications such as SRAM uninitialized states usage in PUF and TRNGs. We can't use them anymore if we reset the entire SRAM at boot. Using memory built-in self-test engine could be a solution though, because it's a hardware solution and it is really fast. If the system designers want to reset the static random access memory at boot time. Then we can think about using trusted execution environments such as ARM Trust Zone to enforce security boundary across temporarily separate system states. Note that the cache extraction runs in the same exception level as Trust Zone, so if an attacker can get to that EL3 level, Trust Zone will not prevent volboot attack. Finally, it doesn't matter if an attacker retains the states across power cycle. He needs to get to the data from the target SRAM. Using mandated boot authentication and protected debug interface should prevent volboot attack. However, sometimes these are not practical and available in all devices. Okay, there you have volboot, an attack that artificially creates SRAM data retention in complex SoC with perfect accuracy for indefinite time. And it does it without having to rely on physical attack vectors like temperature device technology node. Thank you.